You hear that clicking noise? That's the sound of NASA's Perseverance rover zapping rocks on Mars. The rover uses a laser to collect information about the chemical makeup of its targets. This episode of Stereochemistry is all about the red planet and the scientists who study it. Mars has gone through a lot of changes in the last few billion years, and understanding those changes could influence the planning for future crewed missions to Mars, and even how we think about our own planet. To tell us more about this, I'd like to bring in Sam Lemonick, who covers space chemistry at CNN. Welcome back to the show, Sam.
Thanks, Carrie.
So we were just listening to a recording of Perseverance hard at work on Mars. What can you tell us about that rover's mission on the planet?
Right. So Perseverance just landed on Mars back in February, and over the last few months, it's been testing out its equipment and starting to explore. The laser we just heard is part of the rover's suite of instruments for analyzing Martian rocks and soil. These tools can identify molecules at a distance by analyzing the spectrum of light that's produced after Perseverance blasts them with this laser. Perseverance's big mission is to collect evidence about whether Mars was ever habitable, and maybe even find some signs of ancient life if they exist.
And I know that looking for life has motivated a lot of missions to Mars, or at least the question of life has always been in the background, even if a mission's specific objective is different. But I've seen the pictures coming back from Perseverance and other missions to Mars, and they all look like they tell the same story. The planet is dry, dusty, and dead.
Right. Everything we know about what conditions are needed to support life strongly suggests that Mars probably is not habitable right now, and the lack of liquid water is one big reason why. But starting with some of the first missions to Mars in the 1970s, the orbiters, landers, and rovers have been sending back a consistent message. Mars used to be a very different and very wet place. Imagine this. Rivers carving their way through steep, rocky Martian canyons, meandering streams with banks of damp red clay, or a massive ocean covering as much as a third of the planet. These are all possibilities that scientists are exploring based on the data sent back from rovers like Perseverance. In fact, scientists think that billions of years ago, Mars and Earth may have looked a lot alike. Earth, as we know, stayed pretty warm and wet with a nice thick atmosphere. But something happened on Mars, and now it's a cold, dry desert. What happened and why might tell us about how planets evolve. In this episode, we'll learn how scientists uncovered Mars's watery past, and then we'll meet some of the scientists who are trying to find out where all that water went. They'll take us through some of the most promising theories, but I'll warn you, there are some things that still have scientists baffled. As I said in my emails, I'm working on a podcast about water on Mars, and I'm still learning about water on Mars. So my questions...
Everybody is.
Okay, fair. That's Javier Martin Torres, a planetary scientist at the University of Aberdeen in Scotland. He was actually the first person I talked to for this episode. He's been involved in a bunch of Mars missions, and he's in charge of an instrument on the ExoMars rover launching next year. Here's the thing. Scientists still don't know where Mars's water is. Or, to put it another way, they're still finding clues and making predictions and arguing about where Mars's water is. But they know a lot more now than they did 3 decades ago. And with the technology we've been able to land on Mars now, with the Perseverance rover and others, the answers seem closer than ever.
Well, before we hear about scientists' ideas on what happened to Mars's water, I'm really curious about this ancient, wetter Mars. How do we know that Mars used to be so soggy?
To answer that, let me take you back to the 1870s. This was the age of the first telephone call and the development of the germ theory of disease. Also at that time, an astronomer named Giovanni Schiaparelli was looking at Mars through his telescope and drawing pictures of what he saw on the surface. Today, we're used to seeing incredibly detailed photographs of Mars, but with the telescopes of the time, Schiaparelli's view was probably considerably fuzzier than even our view of the moon with the naked eye. Based on what he could see, Schiaparelli formed the idea that there were canals on Mars, huge waterways dug by somebody to move water around on the surface.
So, like, Martians?
Yeah, that was his theory. And the funny thing is that when other scientists like Percival Lowell looked through their telescopes, they said they could see the canals too.
Percival Lowell and Giovanni Schiaparelli were advocating for the idea that there were canals on Mars and there were sentient beings that were transporting water from one place on Mars to another in what they thought might be a drying out planet at that time.
That's Roger Wiens of Los Alamos National Laboratory. He's in charge of the instrument on Perseverance that's zapping rocks to figure out what molecules are in them.
To be clear, these guys were not right about the Martians.
Well, no, they weren't. What those astronomers saw were almost certainly optical illusions. No one had built canals on Mars. But even though they were wrong about that, about a century later, the first spacecraft to orbit Mars sent back some surprising information. Here's geophysicist Elena Pettinelli of Roma Tre University describing NASA's Mariner 9 mission in 1971.
And it's quite strange when we went to Mars with Mariner 9, when we find definitely canals. Something was supposed to be there and wasn't there in reality. It was there.
Schiaparelli's canals were optical illusions, but there were real waterways on Mars. Mariner 9 beamed back thousands of photographs of the planet's surface, and some of them indeed showed water channels, along with other features formed by water, like deltas and meandering riverbeds. This created somewhat of a crisis in the planetary science community. Here's Bethany Ellman, a planetary geologist at Caltech.
This question has been asked since the very first Mariner images showed canyons carved by water, that set people like Carl Sagan and Harold Urey and Gene Shoemaker and all these early giants of planetary science equally scratching their head. Well, what happened?
So scientists had to square what they knew about present-day Mars, dry and cold, with these geologic features that could really only have been formed by rivers and moving water like we see on Earth. Bethany says that's when current ideas about Mars's complex and wet geologic history started to take shape. But scientists would need a lot more data to start filling in the details of how Mars's climate changed and start to answer the questions of where Mars's water went. I talked with Amy Williams, a geoscientist at the University of Florida, to get a better sense of how our understanding of Mars's history has evolved.
It was with each iterative step of a new mission, a new orbiter or lander or rover, that we started to develop a much more complex picture of Mars as a planet.
Amy told me geologists divide Mars's history up into 3 major periods, each with its own distinct conditions. Like Earth, Mars formed about 4.5 billion years ago. Until maybe 3.7 billion years ago, Mars had water. Lots of it.
And we see these features that tell us that there was absolutely just an ocean's worth of water.
Based largely on the size and number of lake beds, deltas, rivers, and other water features, scientists think Mars had enough water to cover the entire planet with somewhere between 100 and 1,500 meters of water. On the high end of estimates, Mars might have actually had more water than Earth, even though Mars has about 1/3 Earth's surface area. So that's our first geologic period.
That's the Noachian. And moving forward in time, we move into what we call the Hesperian. This is sort of that global drying and global climate change that affected Mars.
Amy says that as all that water gradually dried up, it left behind salts and other mineralogical evidence of the planet's watery history. The Hesperian lasted from maybe 3.7 billion years ago until about 2.9 billion years ago. The current period is the Amazonian, which has lasted ever since. That's the Mars we recognize, a cold, dry desert. Too dry to support life as far as we know, but etched with these clues that the planet was once very different, maybe even something like Earth. This is the mystery that has tantalized scientists since the 19th century.
It's a really great way to provide some context for humanity within the solar system and within the universe. There's these two worlds. Did life arise on both of them? Did it die out on one but flourished on another? And perhaps is that life still there, or have other worlds experienced this same shared early history and then this great climatic change that inhibited one world from kind of carrying on in the direction it appeared to be going?
Mars's geological evolution stretches back billions of years, but humans have had the tools to understand its history for just the past few decades.
After the break, we'll dig into what scientists have learned from this new data and how they're beginning to connect the dots on Mars's missing water.
Hi everyone, Gina Vitale here. I'm an assistant editor at CNEN, and I'm here to remind you about a great way to stay up to date with the latest news from the world of chemistry and chemical engineering, our weekly newsletter. The newsletter delivers the best of CNEN to your inbox every week. You'll get the most important research findings, the emerging trends you need to know to get ahead, plus the latest jobs and career insights, and also some really cool extra content, like periodic graphics in collaboration with the science illustration website Compound Interest, or Chemistry in Pictures, which showcases the beauty of the central science. You can sign up for our newsletter at bit.ly/chemnewsletter. Just point us to your inbox and we'll take it from there. Again, that link is bit.ly/chemnewsletter. We'll also include that link in this episode's description. And now, back to the show.
So, Sam, we've heard now that scientists can't yet fully answer the question, where is Mars's water? But clearly we know a lot more about Mars's water today than we did in the 1970s when astronomers were shocked to see evidence that Mars used to be wet. So how much of that question can we answer?
Well, if you're okay with some roughish estimates, you can start to put some of the pieces together. In the early 2000s, scientists sent 2 orbiters to Mars with radar instruments that mapped the surface and what was in the top few kilometers of crust, creating a 3D map of the planet. From that spatial data, scientists were able to calculate the volume of water in Mars's polar ice caps and some ice below the surface at lower latitudes. The problem is, when scientists look at the data collected on Mars and they do some water accounting, they're left with a lot of missing H2O. To help explain this, we'll have to endure some jargon. Remember I mentioned that Mars might have once been covered by hundreds or thousands of meters of water? Well, that's a huge amount of water, and it can be hard to grasp how that compares to, say, the volume of an ice cap. So scientists have a term to help simplify their comparisons: Global Equivalent Layer, or GEL. That term is going to come up a lot in the rest of the episode. It means the amount of water you need to cover the entire surface of the planet.
So a water blanket, 1,500 meters thick, over the entire planet is equivalent to
1,500 meters GEL. That's the top of the range for the amount of Martian water during the planet's wet Noachian period. Scientists think that at a minimum, Mars had 100 meters GEL of water. But ice on Mars today accounts for only about 40 or 45 meters GEL. As for the rest, well, that kind of depends on who you ask. Let's start with the most widely accepted explanation for where at least some of that water went. Scientists think during the Hesperian period, that was the middle period in Mars's history when the planet started to dry out, some of Mars's water started floating off into space. You probably won't be surprised to hear that exactly how that happened is a matter of active debate among Mars scientists. But the basic idea is that the sun's radiation broke water down into H's and O's and blew them off from the top of its atmosphere. Maybe Mars once had a strong magnetic field like Earth's that protected its water molecules from the sun's ionizing radiation, but lost that field somehow over time. Also, Mars is smaller than Earth, so its weaker gravity maybe couldn't hold on to its H's and O's as well. Spacecraft like NASA's MAVEN orbiter can measure how much water is escaping from Mars today. The problem for scientists trying to tally up Martian water, though, is it's not enough. Here's Javier Martin Torres again.
When we look at the data from instruments like MAVEN, we see that even with these facts, it's difficult to explain that the atmospheric escape of water that we observe, they cannot account for the complete mass of water lost.
Scientists are trying to reconcile 2 pieces of information: the amount of water that we think Mars had based on the volumes of the canyons and deltas we've observed, and the rate that Mars is losing water into space. And as Javier said, if the current rate of water loss is extrapolated over Mars's history, it doesn't account for all the water Mars had back in the Noachian period. Models based on current water loss suggest maybe 100 meters GEL of Martian water has wafted out into space, while remember, the upper estimates of Mars's early water are near 1,500 meters GEL. So that brings us back to Bethany Ehlmann and her colleagues at Caltech.
It was mostly sucked into the crust and mostly lost to space.
So this is actually a fairly recent addition to the explanations of Mars's missing water. When she says sucked into the crust, she's talking about water molecules being incorporated into minerals. In April, Bethany, her colleague Eva Scheller, and a few others published a paper in Science suggesting that between 30% and 99% of all the water Mars ever had might still be on the planet, incorporated into the crystal structure of minerals in its crust as water, or hydroxyl, meaning just an oxygen and a hydrogen from a water molecule.
It occurred to my co-author Eva Scheller and I that, hey, wait a minute, has anyone thought about the role of all these newly discovered minerals? What piece do they play in the puzzle? Clearly, they've affected the water balance because there's water and there's OH in the minerals. So they have been a sink over time. Some of the water has been lost to space, some of it's been lost to the ground, and that was the sort of the setup for our paper. How much?
None of the other scientists I talked to dismissed this idea, which at this point is still just a couple months old. In fact, this paper is generating a lot of excitement and discussion among Mars scientists. Here, finally, they might have an explanation for the discrepancy between the amount of water they think Mars had and the amount of water they can account for. Now, I should say that while Bethany and Eva's data and analysis are new, the idea actually isn't. Bethany found a paper published in 1976 by Robert L. Huguenin of the Massachusetts Institute of Technology entitled Surface Oxidation, a Major Sink for Water on Mars, which presented the same basic idea as her group's paper earlier this year.
At the time, he was like, hey, Mars is kind of this rusty, oxidized place. If you sort of, add this all up, it could be a lot. But there was no data at the time to allow you to say, well, how much was trapped? So it took another, 30 years to get the data to actually put the numbers to quantify and constrain the model from just being one of speculation to one being one based on observation.
Now, you'll remember that Bethany's group put a pretty wide range on how much water is locked in the rocks, between 30% and 99%. The reason that estimate is so broad comes back to the question of how much water Mars initially had. Was it on the order of 100 meters GEL or closer to 1500 meters GEL? And there are other sources of uncertainty too, like how much water went where when Mars had volcanic activity. Scientists are trying to balance the books, but that's really tough when there are still these huge gaps in what we know about Mars's past. But I think we can say that about 45 meters GEL is in ice, about 100 meters GEL has been lost to space, and almost all the rest is below the surface, however much that might actually be.
Okay, so there's still some uncertainty, but that's a pretty conclusive picture, right? A little bit in space, a little bit in ice, the rest in the rocks.
Well, it's actually not as tidy as that. There are a few other places scientists think water might be. Probably not a lot of it, but they're worth mentioning. One of the other possibilities is lakes of liquid water, possibly salty brine, beneath some of Mars's ice caps. Elena Pettinelli, who was telling us about Mariner 9, was one of the researchers who first reported a radar signal they interpreted as a 20-kilometer wide lake under the southern ice cap back in 2018. Her group is still working to understand that lake, and they're examining other similar data to see if there are more. And while it's far from certain that anything could survive in these lakes, we do know there are organisms on Earth that can survive in very salty brines. Javier Martin Torres is part of another team also looking into brines, but much closer to the surface, actually on the surface. In 2015, the researchers proposed that perchlorate salt brines could be liquid on Mars's surface under certain conditions. The salt content lowers the water's freezing temperature so it stays liquid even in the frigid climate of Mars. He also thinks those brines could be the source of some seasonal changes scientists have observed on Mars's surface that look like they could be the result of flowing water. And, just to bring it back to the lasers, Perseverance's rover predecessor, Curiosity, had a laser too. The very first time Curiosity fired that laser into the Martian dirt, it saw that the dusty clay the rover was driving through had water in it. Not much, but water all the same. Here's Roger Wiens again. He's managed the laser instruments on both rovers.
But that's a very interesting thing because the amount of water in that soil and dust on Mars is just about equivalent to, say, a soil in southern New Mexico during the summer, which, although that may be a bit of a desert, it's still not one of the driest places on Earth at all.
All right, so it sounds like scientists are off to a good start figuring out what happened to Mars's water. I guess my next question is, do you think we'll ever know for sure?
Well, the scientists I talked to certainly hope so. And one thing that really came across in my conversations with them is just how young this era of Mars research is. I mean, for comparison, we've had a few hundred years to work on Earth's geological history. We're kind of spoiled with all the rovers and orbiters that have been to Mars and are planned for Mars, but it's still just a couple dozen total. We'll probably need new kinds of instruments on Mars, like seismometers and electromagnetic probes, to understand what's happening with water below the surface. And remember that doing science with robots on a planet millions of miles from Earth is really, really hard, even if we're getting good at it. I was joking with Amy about the difference between a Mars rover and a human geologist.
I could, go to Mars, notwithstanding all of the technological constraints of sending humans at this point. I could go to Mars and stomp around and use my rock hammer to take a bunch of samples and use my intuition as a geologist to understand how that landscape formed. But when you're doing it with robots, the way that we are, which is incredibly advanced, and even a few decades ago, we couldn't have imagined that we'd be exploring Mars and many of these other worlds in our solar system the way that we are. It's still constrained.
Now, just in case any Mars rovers are listening, Amy did point out that each of them carries a whole suite of analytical instruments that basically make them mobile laboratories, something no human could ever do. But her point is that we're still forming our hypotheses about Mars's water from tidbits of information that are trickling in at the agonizingly methodical pace of current Mars exploration.
So maybe we'll just have to put out a sequel to this episode a few decades from now.
Yeah, and who knows? Maybe by then you'll have a robot for a co-host. But look, the rovers are going to keep exploring, Perseverance is going to fire its laser, scientists are going to interpret the data, and then other scientists are going to use that information to refine our understanding of the history of water on Mars, and maybe even planets in other solar systems too. Maybe one day we'll have human geologists on Mars who can make other insights that we haven't been able to with rovers and orbiters alone. But we can definitely expect that scientists are going to keep hammering away at that question.
Thank you, Sam.
This episode was written by
Wait. We can't do the credits yet. I have an announcement.
Okay.
Folks, a couple of months ago, we asked for your feedback in helping to shape the future of stereochemistry. And thank you so much to everyone who participated in our survey. We hear you, and we're going to be taking stereochemistry in an exciting new direction. Coming soon will be our first ever season of stereochemistry, a limited series of episodes about a common theme. It'll have everything you love about stereochemistry, fresh research, unique stories, but we'll have a chance to dive a little bit deeper and explore some new angles from industry, academia, and beyond. We'll have more details for you soon. While we put that season together, we'll be taking a break from publishing full episodes of stereochemistry. But we didn't want to leave you high and dry, so we'll have lots of other content coming your way right here in the meantime. So keep an eye on your feed and get ready for the very first ever season of stereochemistry.
I can't wait.
Thanks, Sam. Now, please proceed with your credits.
All right. This episode was written by me, Sam Lemonick, and produced by Carrie Jansen. Story editing by Carrie Jansen and Michael Torres. Production assistance from Gina Vitale.
The music in this episode was Dreaming, Puddles, and Like We Used To, all by Stanley Gurvich, and Floating Point by Roish Bigler. The recording of the Perseverance rover's laser was provided by NASA.
Stereochemistry is the official podcast of Chemical and Engineering News, which is published by the American Chemical Society. Thanks for listening.